Good day, I'm J Wildberger from the School of Mathematics and Statistics, Faculty of Science at the University of New South Wales. This is a research snapshot in which I'm going to try to explain the basics of my book, whose title is Divine Proportions, Rational Trigonometry to Universal Geometry. So it was written in 2005 and published by my own little company called Wild Egg Books. So this book lays out a new foundation for trigonometry and thereby allows a new formulation for Euclidean geometry, which widely extends it. So in today's little presentation, I'm going to tell you some basics about rational trigonometry. Okay, so rational trigonometry is a purely algebraic form of trigonometry that extends to general fields and avoids entirely transcendental functions like cosine, sine, tan, and so on. You might think it'd be impossible for trigonometry not to involve those very familiar functions, but in fact it is possible, and it turns out to be a big improvement. What is universal geometry? By that I mean the extension of Euclidean geometry to a much wider and more embracing setting. Namely, I want to extend Euclidean geometry so that it works over general fields, in particular over the rational number field, which from my point of view is the sort of fundamental framework that we should be aiming towards understanding first, but also to finite fields. And moreover, it extends the subject to include arbitrary quadratic forms, not just the Euclidean one. So it turns out that the main laws of the subject are valid also for relativistic geometry. So this is an attempt to encompass both Euclidean and relativistic geometries in the same framework so that the same theorems will apply uniformly across the board. My book also has some applications to, first of all, classical Euclidean geometry, engineering and surveying problems, physics, chemistry. And then there's interesting applications to computer graphics, and there are even robotics teams which are using rational trigonometry these days. But I think it's fair to say that the killer application is still in the future and is with the education of young people. Trigonometry is a barrier to the further development mathematically of many young people. And I can sympathize with them because the trigonometry that they are currently taught is logically weak and overly complicated, really. And when you actually look at it carefully, the number of examples is quite restrictive. It turns out that when you do classical trigonometry, you do over and over again the 45, 45, 90 triangle, with sides 1, 1, root 2 in terms of distances, angles. Or you deal with the 1, 2, root 3 triangle with angles 30 degrees, 60 degrees, and 90 degrees. It's not much of an exaggeration to say that even for undergraduate math majors, these are really the only two triangles that their current technology of trigonometry allows them to really adequately deal with. And you wouldn't believe the amount of machinations necessary for teachers, both undergraduate and high school teachers, in order to cook up examples that almost essentially always involve these two triangles or variants of them. Okay. So the current trigonometry is in fact quite limiting, and with rational trigonometry we have a much broader vista. So let's have a look at the details. What actually is rational trigonometry? How does it work? My book presents the theory of rational trigonometry to an essentially high school audience. So it relies only on elementary Cartesian geometry. But if you have a little bit of linear algebra under your belt, it's easier to explain it using a bit of linear algebra and the familiar dot product between two vectors in the plane. Right. So the main notions are quadrants and spread, which replace the usual distance and angle. And I remind you that Euclid carefully avoided distance and angle because of the foundational difficulties with defining those things correctly. hope you realize that when you actually work with angles, implicitly you have a prior theory of calculus involved in order to define the arc lengths of those arcs of circles that are implicitly involved. So here we avoid any mention of these transcendental things. There's no calculus required. It's just all elementary high school algebra based essentially on the quadratic form. Okay, so the quadrants of a vector is by definition v dot v. That's all. And the spread between two vectors, v1 and v2, is defined in this way. 1 minus v1 dot v2 all squared over the quadrants of v1 times the quadrants of v2. And you can think about the quadrants of v1 and v2 down here as being normalizing factors to ensure that this spread is independent of scaling of v1 and v2. Now, if you have been taught traditional trigonometry, as I know you all have, you will recognize this as the square of the length. And this is, well, this is the cosine of the angle squared, so this is really the square of the sine of the angle. And that's another way of thinking about spread, if you already know about angles and you already know about the transcendental function sine. But it's better to forget about that prior theory and just think about this as being the basic definition, purely algebraic. All right, so just as an example, here are three vectors. v1 is 2, 1, v2 is 1, 3, and v3 is 2 minus 3. And these three vectors make also three spreads. So the spread between v1 and v2, we might call that S3, and here's my notation for it. Also note my notation for the quadrants is, I should have put a Q3 over here. Let's do that. There's the quadrants Q3. So we have the spread S3 between these two vectors, the spread S2 between v1 and v3, and the spread between v2 and v3 would be the spread S1. All right, so the quadrants of the vectors, just sums of squares of coefficients, 5, 10, and 13. The spread S3, for example, is 1 minus, take the dot product, which is 2 plus 3, that's 5. You have to square it, and you divide by the product of the quadrants is 5 and 10, for a total of 1/2. And 1/2 corresponds to an angle of 45 degrees, or pi on 4, if you like. The spread S2 between v1 and v3 turns out to be 64 over 65, which is almost equal to 1. Spread of 1 would be perpendicular. And the spread S1 is 81 over 130. And you can see that you can calculate spreads easily, and you don't have to restrict yourself to any particular simple kinds of triangles. Take any 3 points in the plane, you can calculate the quadrants, you can calculate the spreads. And here is a general triangle, and here are the three main laws of rational trigonometry, which replace all those laws of classical trigonometry that students learn in high school and spend years learning. So in terms of the three quadrants, Q1, Q2, and Q3, and the opposite spreads, S1, S2, and S3, we have the cross law, which is the most powerful law. Q1 plus Q2 minus Q3 squared equals 4 Q1 Q2 1 minus S3. We have the spread law, which replaces the sine law. S1 over Q1 equals S2 over Q2 equals S3 over Q3. And then the most interesting one is the triple spread formula, which tells us the relationship between the three spreads. This is an analog of the fact that the sum of the angles is, what is it, 3.1415926, etc., 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 to infinity. Much, much simpler. Although it's a cubic altogether, in fact, it defines a very beautiful and interesting cubic surface. So algebraic geometers might want to investigate this object. Very interesting. So these are the main formulas of rational trigonometry. And armed with these, we can go out and solve all those engineering and surveying problems. And typically, this is the important thing, we can do so without resorting to a calculator. Basically, all we have to do is be able to solve a quadratic equation. And we can do so with pen and paper. And invariably, we can do things faster and more efficiently. And we can deal with all kinds of different situations with complete accuracy. We don't have to just rely on decimal approximations. So that geometry becomes an exact science, which is really what it ought to be. There are about 120 theorems in my book, and it's clearly not possible for me to tell you about all of them, although most of them are novel and pretty interesting. But there's a few points that I think need to be mentioned because they really lead to new directions. And one of them is this theory of spread polynomials that's intimately connected with rational trigonometry and seems to open up a new chapter for theory of special functions and orthogonal polynomials. So very closely connected with the Chebyshev polynomials, but they have some remarkable additional features. And they arise rather simply. If we have, say, 3 lines, and we know this spread between these 2 lines is S, and we know the spread between those 2 lines is also S, it's natural to ask what is the spread between the 2 outside lines. And we might call that S2 of S. It's not too hard to show, using that triple spread formula that I wrote down, that in fact S2 of S is the function 4S times 1 minus S, which you'll recognize perhaps as being the logistic map from chaos theory. And similarly, you can then extend this to, say, 3 equal spreads of S and ask what's the sort of composite spread, and you get the 3rd spread polynomial and so on. So you get a very interesting family of polynomials whose graphs turn out to bounce around in the square 0, 1, 0, 1, much as the Chebyshev polynomials do. But my student Susheng Go, in his honors thesis, made the lovely observation, which I describe in my book, that these spread polynomials have factorization properties which are more beautiful than the Chebyshev polynomials. And so, so I think there's a lot of work to be done in trying to understand these spread polynomials. I want to just sort of show you a few assorted theorems from my book to give you a flavor of how rational trigonometry works. I hope you appreciate the absence of any transcendental quantities here. Okay, so the first one is just dealing with a simple isosceles triangle with quadrances Q, Q, and Q3, say, and spreads, equal spreads here of S and S, and spread of S3 up here. And we might ask, how do we get spread S3 if we know the 3 quadrances? Here's the formula. S3 equals Q3 over Q times 1 minus Q3 over 4Q. Here's a classical theorem called Stewart's theorem, rewritten in the language of rational trigonometry. And if you look at the formulation here, you'll see it's reasonably different from the classical formulation. It involves an arbitrary triangle with quadrances Q1, Q2, and Q3, and a point down here somewhere, so that we have quadrances R1 and R2 down here, and quadrants R3 up to the 3rd vertex. And then there's a relationship between these quantities, and it's given by R2 times R1 plus R3 minus Q2 squared equals R1 times R2 plus R3 minus Q1 squared. Here is a sort of practical application of a bug crawling up an incline. So we imagine we have an incline here. This is horizontal, and this is an incline, and the incline makes a spread of S with the horizontal. And the bug, it does not want to go straight up the incline because that's too steep, and so it climbs at some spread to the steepest direction, say a spread of R. And we're interested in asking, okay, what is the now the spread that that bug makes with the horizontal? It's presumably decreased, it's no longer S, it's something less, and it turns out to be very simple. The new spread with the horizontal is the old spread times 1 minus R. So you get lots of elegant formulas like this. Here is one more. That's a classical surveying problem. So you're on a train, you're a surveyor, and in the distance there's this mountain. You like to figure out how high the mountain is, but you have no way of getting to the base of this mountain. But there's the base of the mountain, and here's the train that you're on. And so what you do is you make 3 observations of spreads elevated from the horizontal to this point B, the top of the mountain. So you make 1 observation at A1, 1 observation at point D, and 1 observation at A2. And we can also suppose that we know the quadrances here along the train track. And the aim is to calculate the quadrants H of the height of that mountain. It's a lovely exercise. If you haven't seen this problem before, you might like to try it with classical trigonometry and see how you go. Anyway, so you can see that the formula for h is a quadratic formula, and in fact, maybe not surprisingly, it actually uses Stewart's theorem. It involves the three spreads R1, R2, and R3, the reciprocals, and these two quadrants is P1 and P2, of course, to give us a quadratic equation. And finally, I'd like to just point out a lovely fact that is in the last chapter of my book, where I talk about the Platonic solids. So with rational trigonometry, we now have at our disposal the tools to investigate these things much more deeply, because we're not just interested in approximate values for things like distances and angles. We want to know exact values for quadrances and spreads. And so a natural question is, if you have, say, a dodecahedron, and you take two adjacent faces, what is the separation of those two faces? In rational trigonometry, we ask, what is the spread between those two faces? And the answer is, as I compute in the book, 4/5. So lovely, that is a rational number. For an icosahedron, it turns out to be 4/9. And for a tetrahedron and an octahedron, it turns out to be 8/9. For a cube, of course, it's 1. So it's lovely that those rational numbers are occurring there. So rational trigonometry has a lot of other implications. It allows us to rethink hyperbolic geometry, and that was really my main direction of research after I wrote the book. But I'm still waiting for my mathematical colleagues around the world to catch up, right, and to start appreciating just how powerful rational trigonometry is, what huge potential it has to not only transform subjects like algebraic geometry and a lot of application-oriented subjects, but also, and perhaps more importantly, it allows us to rethink mathematics education and to lay out a simpler and more natural and more beautiful way of introducing young people to trigonometry.